let V be the vector space of all real polynomials of degree less than equal to 3 together with the zero polynomial over the field R. These are the two subspaces of V given to us. W1 is having all those polynomials belonging to V such that f of 1 equal to 0. W2 is having all those polynomials belonging to V such that f dash 1 is equal to 0. We need to find the basis and dimension of their intersection, right? And also we need to extend the basis of W1 intersection W2 to the basis of V, right? So let's take one polynomial from their intersection and let that polynomial be a plus bx plus cx square plus dx cube belonging to their intersection. Why I stopped at x to the power 3? Because I'm having V to be the vector space having all the real polynomials whose degree is less than equal to 3. So we need to stop over here only. What are the conditions? For W1, F1 equal to 0 and for W2, F dash 1 equal to 0. And because we are working on the intersections of the subspaces, so we need to have these two conditions both. Okay. F1 equal to 0 implies, just put x equal to 1 over here, we get a plus b plus c plus d equal to 0. From here we get the value of a to be as negative of b plus c plus d, right? From the second condition we are having f dash 1 equal to 0. For that we need to get f dash x first, the derivative of fx with respect to x. So we are having this to be as b plus 2cx plus 3dx squared. And f dash 1 becomes b plus 2c plus 3d and is equal to 0. So from here we can get the value of b to be negative of 2c plus 3d. Let's put this value over here. So we get this to be as negative of 2c plus 3d plus c plus d. That is negative of, minus 2c and plus c. This becomes negative c. And minus 3d plus d becomes negative 2d. So that is c plus 2d. And if we write back this polynomial, just put the value of a this. So we are having c plus 2d plus bx. For b I am writing this. So this is negative sign 2c plus 3dx plus cx square plus dx cube. So taking c common first, we get 1 minus 2x plus x squared. And if I take d common, we get 2 minus 3x plus x cube. So what we notice here, that this fx is a linear combination of these two polynomials, right? And because fx was arbitrary, right? So every polynomial belonging to the intersection of the subspaces is a linear combination of these two polynomials. So let's write this as fx is a linear combination of, yes, x square minus 2x plus 1 and x cube minus 3x plus 2, right? But fx was arbitrary. So therefore every polynomial of their intersection of subspaces is a linear combination of these two polynomials. That means the intersection of W1 and W2 is generated by these two polynomials, right? And because these two are not multiple of each other, so that means these are also linearly independent. So since the polynomials are not multiple of each other, so these polynomials are linearly independent, right? So the basis of W1 intersection W2 becomes x square minus 2x plus 1, x cube minus 3x plus 2. So these are the bases, and dimension of their intersection is how many number of elements? 2. So the dimension is 2. And now we need to extend these bases to the basis of V. Okay, what is the dimension of V? Yes, V is a set of polynomials of degree less than equal to 3. So what are the standard ordered bases of V? X cube, x square, x1. These are the ordered bases of V, right? So the dimension of V is 4 because the number of elements in the ordered bases are 4, right? To form the basis of V, the number of linearly independent vectors should be equal to the dimension of V, right? Now already these two polynomials are linearly independent and also the subset of V. Why? Because these two polynomials are the basis of W1 intersection W2. That is why these two polynomials also becomes the subset of V. These are linearly independent. But I need the number of linearly independent vectors to be 4 because of the dimension of V, right? What other polynomials I can add to extend the basis of W1 intersection W2? So we can have the polynomial to be as x and also a constant polynomial, that is 1. We can take this one to be as x to the power 0. And now these set of polynomials are linearly independent. Why? Because none of the polynomials is a linear combinations of the preceding polynomials. The degrees of the polynomials are increasing in number. Here we are having the degree 1. Here we are having the degree 0. Here we are having the degree 2 and 3. So none of these polynomials are the linear combinations of the preceding ones. So these polynomials are linearly independent. And also the set of these polynomials are the subset of V, right? As these are linearly independent, also belonging to the subset of V, number of elements of these polynomials are also 4. And the dimension of V is also 4. So definitely this set of polynomials becomes the basis of V. As the dimension of V is 4, therefore this set of polynomials is a basis for V. Please remember, if the number of linearly independent elements which are the subset of V is equal to the dimension of V, then this set of polynomials becomes the basis for V, right? So already these two are the basis of W1 intersection W2. And we have shown that by adding other polynomials to these bases, the complete set again becomes linearly independent, right? Also the subset of V, and the number of elements present in this set is equal to the dimension of V, that is 4. So definitely all these polynomials becomes the basis for V. So we have extended the basis of W1 intersection W2 to the basis of V, right? Okay.